Dynamics of a Spring Projectile Launcher by Brent Williams, Jacob Engelbrot, Ted Shipley, and David Colon. Purpose. Our purpose of the project was to determine the spring constant K in a self-designed and built spring projectile launcher. Using kinematics of the spring launcher and conservation of energy equations, we could calculate the approximate value of the spring constant. Background. We brainstormed a lot for this project, and eventually we happened upon the idea of calculating the value of a spring constant. During this brainstorming, we realized that springs were found everywhere around us, and they are really important for many different machines and mechanisms found throughout the world today. When thinking even further, we came to the conclusion that we could calculate the spring constant in a launcher using kinematic equations we learned early on in the semester. Therefore, by analyzing the kinematic motion of the projectile and the energy conservation in the spring, our group could calculate the theoretical value of our spring projectile launcher. Design. First, we had to design the spring launcher we would use. We started this by 3D printing some of the parts and using a PVC pipe as the shaft. Once all the pieces were ready, we constructed the spring launcher very carefully. Then we were ready to use it to calculate the spring constant K and launch our projectile, a 12-sided dice with a mass of 0.0218 slugs. And here on the left you see the spring launcher disassembled with all of its parts, and on the right is the spring launcher assembled. Method. To start recording results, we set the launcher up on the edge of a table and pointed it at an angle of 9.81 degrees above the horizontal. After setting up the launcher, we took the velocity measurements of 3 different compression lengths. First, when x is equal to 0.8 inches, second, when x is equal to 1.1 inches, and third, when x is equal to 1.4 inches. During the launch, we used Tracker to record and model the kinematic motion of the projectile. After the motion was tracked, we graphed it and used the conservation of energy equation above to calculate the spring constant K. Results of motion. Here on the left you see launch 1 results when the compression length was equal to 0.8 inches. And on the right, launch 2 results when x is equal to 1.1 inches. For launch 1, the max velocity was the initial velocity at 83.7 inches. And launch 2, the max velocity was 87.26 inches per second. However, this was not the initial velocity. And third, when the compression length was equal to 1.4 inches. Here we found the max velocity to be 154.5 inches per second. Over the past 2 slides, we saw the measurements of the 12-sided dice projectile. You can see that as the spring compression distance increases, the velocity tends to also increase. Additionally, we observed that the highest velocity was not always at the start of the launch. This was due to possible limitations and error within our launch. One possible limitation we found might be that tracker technology could be slightly off on measurements. Next, we will use our governing equation to calculate the spring constant that we have. Results and analyst K value. After recording the results from the launch, it was time to take the data that we had and plug it into our equation to calculate the spring constant K. The theoretical K that we calculated was 3,575 newtons per meter. We decided, for the sake of accuracy, to throw out launch 2 because it seemed as an outlier. Results analysis K value. Our spring constant of 3,575 newtons per meter seemed somewhat high to the group. However, due to the conservation of energy, it did make sense in our equations. In the first launch, we equated the total energy to be 0.7187 joules, the second to be 0.7811 joules, and the third to be 2.3158 joules. This is the right amount of energy that takes place in a launch such as this one. However, possible errors could have been overlooked in our project. For instance, energy lost due to friction inside the PVC shaft was not taken into account. The energy that was lost could have altered our overall results. Also, we assumed no rotational kinetic energy from the 12-sided dice projectile. We assumed that the projectile remained still and without spin in its flight. Additional errors in our calculations could take place in the recording of our velocity calculations. Multiple tests help prevent extreme room for human error, but we cannot expect manual timing and measuring to be 100% accurate. User error in software and limitation with our camera's frame rate also add to the standard error in our calculations. However, being aware of these and taking the necessary steps helps to minimize the error differentials. Conclusion/recommendation. We concluded that our spring constant was more than likely higher than the actual value of the spring. However, using kinematic motion and the law of conservation of energy, we were still able to get a relatively accurate value of K. Early on in the project planning, we had some challenges with getting accurate readings from the tracker technology. We came together as a team and figured it out in the end. We were successful in obtaining our value, and though the value might be somewhat high, we completed our purpose to analyze the energy and kinematics of our launcher. Recommendation: energy is lost and gained in so many ways, especially in experiments like this very one that we performed. We recommend that you isolate all errors possible so the readings that you get will be as accurate as they can be. Thank you.